In the last video, I've talked about how to derive this formula where we can calculate the force on a charged particle if we know the velocity, the charge, and the magnetic flux density. But this is not the only way to write this formula. Another way, if you look at a textbook in which it can be written, or just one of another way. If you look in a textbook, you might see, for example, this. Big F equals to B times Q times V. Right, if you see this, the F here does not mean the same as this F. It does not mean the force on all the electrons. Right, in this context, right, if you have a BQV here with the velocity, the F here should mean just the force on that single charge. And the Q here means the charge on a charged particle, not necessarily an electron. It can be a proton. It can be a glass ball with some charge on it. So it means that this equation can be used not only for electron, but for any charged object that is moving. Okay, so for example, if I have a glass ball here, if I have a glass ball with some negative charges, and this glass ball is moving with a certain velocity v in, let's see, in a magnetic field V, then there would be a force acting on it. So this is a glass ball. Okay, so this is just to emphasize that it doesn't have to be an electron. It can be any charged object. And there is another detail which we should include in this, and that is the angle. The angle between the magnetic field and the current. Now this angle, if you recall from an earlier video, if this angle is not 90 degrees, if this angle is not 90 degrees as I seem to show here, if it is at some other degrees like maybe 30 degrees, some acute angle, or even obtuse angle, then to this formula we must add the factor sine theta. Okay. Now, if this is the case, if I have an angle different from 90 degrees here, then the steps here where I derived this force for one charge, or for one electron, or for a charged particle, I must include sine theta in all the steps. Okay, so for example, I should have sine theta there, should have a sine theta there, I should have a sine theta here, I should have a sine theta here, and a sine theta here, and a sine theta here, and a sine theta here. So just a straightforward including of the sine theta factor all the way down to here. So this then would be a more complete formula that we can use. And in this case, previously the theta here is the angle between the wire, or the current, and the field. But in this case, the angle here is the angle between the velocity and the field. Now let me draw this out again, just to make sure that it is quite clear. That's the field, that is the velocity here, that's the velocity here, and that's the force there, then the angle theta would refer to this angle, in this case, between velocity and the field. Okay. Now the last thing that I want to talk about here is about the direction of the force. Now coming back to this wire or rod with a current, if you remember, when we know the direction of the magnetic field and the direction of the current, we can find the direction of the force, of the magnetic force, using Fleming's left hand law. Now in Fleming's left hand law, we have to stretch out our left hand. We have to stretch out our left hand, and with our the thumb and first two fingers stretched out. Now the first finger must be pointing in the forward direction of our hand, and it must be pointing in the direction of the magnetic field. So that would be our first finger. Okay, I don't think I'll try and draw my left hand again. The middle finger, or the second finger, is here. I'll point the direction of the current, and the force would then be the direction of our thumb, of the thumb of my left hand. So this is how we would determine the direction of the force. But what if we are talking about just a single charged particle? If you compare this with this, or this with this, we've already seen that the electron moves in a direction that is opposite to the conventional current. So obviously, the Fleming's left hand law is not going to work on the electron, because the velocity is opposite. So what do we do? Do we maybe change hand? Maybe use our right hand instead of our left hand? We can do that, but the way it is normally done is that we still use our left hand, except that we have to have one additional step. Right? We do something before we use our left hand. We say that because the electron is negatively charged, okay, when we apply the left hand law, we must imagine that an electron moving in one direction, a negative charge moving in one direction, is equivalent to a positive charge moving in the opposite direction. Okay, so when applying the Fleming's left hand law to the electron, we must point our second finger, our middle finger, in a direction opposite to its velocity. So let me try and draw this out. Now I'll do it for two cases where I have a negative charge and when I have a positive charge. Okay. Suppose that the magnetic field is in this direction, it's downwards. Suppose that the velocity of the negative charge is in this direction. Velocity of the positive charge is in that direction. We have seen from let me use light blue for this. That's B and that's V. And suppose that we have already seen from the example with the iron rod that the force would then be in this direction. So we have seen that if we have a negative charge moving in this direction, then the force is in this direction. Okay, and we have already, and it was obvious from the rod that Fleming's left-hand law is not going to work because the current actually flows in this direction. Okay, so what I wanted to explain just now was that if you have a charge going in this direction and you want to find the force, the direction of the force, what you can still do is this. We can just use the Fleming's left-hand law, but we take the current direction to be the direction that is opposite to the velocity of the negative charge. So that's the only additional step that we need to make. Okay, and we can get used to this by thinking that by thinking that the magnetic effect or the magnetic force that we get for a negative charge moving in one direction, right, is the same as the magnetic effect or the force if we have a positive charge moving in the opposite direction. So when a charge moves one way and we get a force in this direction, then if an opposite charge moves the other way, then we will still get the force in the same direction. Okay. Conversely, if I have a negative charge moving one way, then when that negative charge is moving this way, the field, I still keep the field in the same direction, new direction of the negative charge. So in the opposite way to this, then we would expect the force direction to also become opposite.